Dear students, let us we study about today the molecular orbital theory in covalent bond. We have studied the other theories in the earlier classes. To explain the covalent bonding, the initially Lewis explained the formation of a covalent bond, and that theory is called the Lewis theory. Then we have studied the valence bond theory, where it explains covalent bond is formed by the overlapping of atomic orbitals. The later on this theory was extended by introducing the idea of hybridization to explain the various structures of the molecules. Earlier to this, the one more theory was introduced called the VSEPR theory, which suggests the structures of various covalently bonded molecules. Today, we study another theory called the molecular orbital theory of covalent bond. This theory was proposed by Hunt and Mulliken in 1932. According to this theory, when atoms combine to give molecules, the atomic orbitals lose their identity and they combine to give a new set of orbitals called molecular orbitals. The valence bond theory says the covalent bond is formed by overlapping of atomic orbitals. But this theory says not only they overlap the atomic orbitals, they combine to give a new set of the orbitals called molecular orbitals. A molecular orbital is a region in space in which the probability of finding the electron maximum. Let us study some of the silent features of molecular orbital theory. The first one, just like the electrons in an atom are found in atomic orbitals, the electrons in a molecule are found in molecular orbitals. The second one, the molecular orbitals are formed by the combination of atomic orbitals of comparable energies and proper symmetry. The third one, an electron in an atom is under the influence of one nucleus, whereas electron in a molecule is under the influence of two or more nuclei. An atomic orbital is thus monocentric and molecular orbital is polycentric. The fourth one, the number of molecular orbitals formed is equal to the number of combining atomic orbitals. If two atomic orbitals combine, it results two molecular orbitals, namely bonding molecular orbital and anti-bonding molecular orbital. Bonding molecular orbital is formed by the additive overlapping of atomic orbitals. Anti-bonding molecular orbital is formed by subtractive overlapping of atomic orbitals. The fifth point, the bonding molecular orbital has lower energy than the atomic orbitals, hence greater stability than the corresponding anti-bonding molecular orbital. The molecular orbitals are filled by electrons in accordance with Aufbau principle, Pauli's exclusion principle, and the Hund's rule. So these are the various silent features of molecular orbital theory. The formation of molecular orbital can be explained on the basis of principle of linear combination of atomic orbitals. It is also called LCAO. Now let us study what is this linear combination of atomic orbitals. The molecular orbitals are formed by the linear combination of the wave functions of the participating atomic orbitals. They may combine either by addition or by subtraction. Let psi A and psi B represent the wave functions, or it is also called amplitude of the two combining atomic orbitals A and B taking part in chemical combination. This combination results in two ways. One is additive combination, another one is subtractive combination. Let us study the first one, combination by addition. In this type of combination, the two waves are in phase. The two electron waves reinforce each other due to the constructive interference. The molecular orbital formed by the combination of addition of wave functions of the two atomic orbitals is called bonding molecular orbital. The wave function of the bonding molecular orbital is given by psi AB is equal to psi A plus psi B. This is called symmetric combination. Students, the plus sign is concerned not to the mathematical way, it is called symmetric or additive. Suppose if you consider the wave function, the psi A, so the upper part we give it a positive sign and the lower part we give it a negative sign. If a positive sign of the amplitude adds to the positive sign of the amplitude, then it results additive combination. So in the diagram, amplitude of the wave increases. And this type of combination is also called symmetric combination. There is another combination called subtractive combination. In this type of combination, the two waves are out of phase. The two electron waves cancel each other due to destructive interference. The molecular orbital formed by the combination of subtraction of waves functions of the two atomic orbitals is called anti-bonding molecular orbital. The wave function of the anti-bonding molecular orbital is given by psi star AB is equal to psi A minus psi B. This is called asymmetric combination. Suppose if I take the wave, so the amplitude of the wave of one is written positive, another is written negative. Suppose if the positive amplitude mixes with the negative amplitude, it results subtractive combination or asymmetric combination where the amplitude, the total amplitude decreases. So this is called anti-bonding. The result of this is anti-bonding molecular orbital. The probable electron density is given by the square of the psi, that is psi square, and not by only the psi. Therefore, on squaring the above equation, we get psi square is equal to psi A square plus psi B square plus 2 psi A into psi B, and psi star square is equal to psi A square plus psi B square minus 2 psi A into psi B. Here psi A square and psi b square represents the probable electron density in the two atomic orbitals, whereas psi square and psi star square indicate the electron density in the two molecular orbitals. In the bonding molecular orbital, the electron density is located in the internuclear region. So, the electrons in bonding molecular orbital bind the nuclei and show bonding effect. In the anti-bonding molecular orbital, the electron density is located in the region on the either side of the nuclei. There is a nodal plane in the internuclear region. So, the electrons in anti-bonding molecular orbital do not bind the nuclei and do not show bonding effect. The attractive interaction is more in bonding molecular orbital, whereas repulsive interaction is more in anti-bonding molecular orbital. Bonding molecular orbital has lower energy and higher stability than the atomic orbitals combined. And anti-bonding molecular orbital has higher energy and lower stability than the atomic orbitals combined. So this is shown with the help of a diagram. Suppose if the 1s orbital of one atom mixes with 1s orbital of another atom, it results sigma bonding molecular orbital, which is having lower energy than the atomic orbitals, and also it results the anti-bonding sigma star 1s anti-bonding molecular orbital having higher energy than the atomic orbitals. The electrons in bonding molecular orbital stabilize the molecule, whereas the electrons in anti-bonding molecular orbital destabilize the molecule. Thus, when two 1s orbitals combine, two molecular orbitals sigma 1s and sigma star 1s are formed. Now let us study what are the conditions for the combination of atomic orbitals. For the formation of molecular orbital, number 1, the combining atomic orbitals should have comparable energy. That is, 1s orbital can combine with 1s orbital but not with 2s orbital. The second one, the combining atomic orbitals should have the same symmetry about the molecular axis. Example, 2pz orbital can combine with 2s orbital or another 2pz orbital but not with 2px or 2py orbitals. The combining atomic orbitals must overlap to the maximum extent. This is the slide that shows when the two hydrogen atoms, the electrons in hydrogen atoms are present in the 1s atomic orbital. So these 1s atomic orbitals, when they combine, overlap and combine to form the new molecular orbital, it results sigma 1s bonding molecular orbital and sigma star 1s anti-bonding molecular orbitals. And totally the 2 electrons are there. These 2 electrons goes to the bonding molecular orbital. Therefore, here you don't have any electrons in anti-bonding molecular orbital. So this is the diagram what I have explained is shown here. The hydrogen molecule is formed. So in the hydrogen molecule, we have the 2 electrons in bonding molecular orbital. Now coming to the shapes of molecular orbitals. We know that the s orbitals are spherical in shape, p orbitals are dumbbell in shape, d orbitals are double dumbbell in shape, and f orbitals are complicated in structure. Now, in the s orbital, when two 1s orbitals comes nearer to each other, these two orbitals, if the positive part of the 1s orbital comes to the positive part of the another, it results bonding molecular orbital where between the two nuclei there is a very high electron density. Whereas the positive part of the 1s orbital, if it combines with the negative part of the another 1s orbital of another hydrogen, then it results anti-bonding molecular orbital where between the two nuclei of combining atoms we don't have any electron density. So the two diagrams, they show the same thing. Now coming to here this diagram shows the bonding and anti-bonding molecular orbitals which are formed by the combination of the p orbitals. Here the p orbital is dumbbell in shape which contains the two lobes. Here I have shown the one lobe is brown in color, another lobe is blue in color. When two brown colored lobes of the p orbital combine, this results additive combination and bonding molecular orbital results. That is the shape which is given in the structure. Similarly, if brown colored bonding molecular atomic orbital, if it overlaps and combines with blue colored atomic orbital of another, this results subtractive combination and forms anti-bonding molecular orbital. So that will be the shape of anti-bonding molecular orbital of the p orbital, the p molecular orbitals. In below, if the two p orbitals, if they overlap laterally, it results pi molecular orbitals. In bonding pi molecular orbitals, electron density is there between the two nuclei which is above and below the plane of the molecule. In case of the anti-bonding pi electron, so between the two nuclei we don't have any electron density. So that will be the shape of the pi bonding molecular orbital and pi anti-bonding molecular orbitals. So the slide also shows the similar explanation what we have discussed. So how the p orbitals are involved to form sigma molecular orbitals and p orbitals are involved to form pi molecular orbitals, both bonding and anti-bonding. It also gives the combination of s orbitals resulting bonding and anti-bonding molecular orbitals. So this is another slide which shows the shapes of the molecular orbitals. Students, go through these things and try to understand the remaining the molecular orbital theory. In the next class, we will study the extension of this molecular orbital theory, so that we call it as molecular orbital theory part 2. Thank you.